I'm Rita Boyd, the Ed Tech Coordinator for the Vail School District. I work with the technology team and the curriculum team, and I'm really excited today to talk about one of my all-time favorite concepts, which is computational thinking. This is a problem-solving strategy that students can use really in any subject area for any class. So as long as you are posing problems and questions for your students to solve, which if you're a teacher, hopefully you are, then your students can actually use this process. This is the process that computer scientists use when they're writing code or debugging code. So it's really important that our students learn how to use this way of thinking, especially if we want them being those 21st century thinkers. So a lot of the jobs that our students are going to have when they grow up are probably going to include technology in some way, right? I mean, they already do. So computational thinking is going to be really prevalent for adults now, as well as for the students who are growing up and going to be entering the workforce. So we're going to talk a little bit about how to use this way of thinking with your students, whether they are kindergarten students or 12th grade students, and whether you teach math or English or social studies or science or some other concept. So let's really dive in. We're going to talk a little bit about the why of computational thinking, so why it's something that you should do with your students. A lot of times in education, we learn these buzzwords or these phrases, and they come and they go, and it might be like, why learn another thing? Which I totally get, and I've been there too. But I'm hoping that you'll kind of see the relevance of computational thinking and how even if you don't use technology at all in your classroom, how just using this way of thinking can help us promote critical and creative thinkers. Once we define computational thinking, we'll also look at the components and give some examples in different subject areas on how you can get started in your classroom using these concepts. We do have a computational thinking team at the district, and it's kind of growing and coming back, but if you are a coding club advisor or if you're really interested in computer science, we would love to have you on our team. Basically, the team works to create opportunities for staff and for students to expand authentic learning. We want to give students opportunities to really be innovative and be critical and creative thinkers, and we really think that computational thinking is just one really accessible way to get students and teachers on board with this higher level of thinking. So the goal at the end of the PD today is that you'll be able to implement some of these ideas in your traditional classroom. So to really enhance what you're already doing with students, it's another tool for your toolbox. So it's not meant to kind of replace what you're already doing. You don't need a whole new curriculum or anything like that. This is something that you can just kind of add to your repertoire and just have as another way to engage your students. So I also kind of want you thinking throughout this lesson, how can you use these components in an unplugged lesson? So you don't necessarily have to use technology to be computational thinkers. So especially if you're kind of at a lower grade level, or if you're a teacher who maybe doesn't use the technology very often, don't check out. This is something you can totally do with your students. So we're going to talk a little bit about that unplugged piece and give some unplugged examples. And then I just really want you to keep that thought in the back of your head, like why? So why should I be doing this? Why is it important for my students? So computational thinking is on the left there. There's some key concepts. It's kind of broken up. It's a problem-solving strategy, essentially, and it's just a way of thinking. So if I'm posing a question to you, or if I'm posing a problem, we probably go through these processes already, but didn't even know. So giving vocabulary and giving words for students to be able to explain their thinking is critical. So here's some big ideas that kind of go alongside with computational thinking. So it is a skill that your students can use really in any subject area for any type of problem. Just giving that common language to students will really help them adapt to new ways of thinking and strategizing when it comes to problem solving. So when we go through those four main components and define them and give some examples, students will be able to use that way of thinking and use those strategies really in any subject area. So it's just a problem-solving method that can be used. You can explicitly model these things in your teaching. So whether you're teaching routines and procedures at the beginning of the year or even doing review. These are things that you can kind of model and show students. So kind of those think alouds that we do so often, they're so valuable. So when our students can really hear what we're thinking and how we thought about something, that really promotes thinking in our students. So we can use some of this vocabulary to better explain to students what we're thinking and how we're solving problems. Like math, where we problem solve all the time, you'll see as we go through the slides that computational thinking kind of lends itself more naturally to math, and you might kind of see that as we go through some of the definitions. But really, I'm going to focus more on some of those non-traditional subjects to really kind of broaden your perspective and give some other examples of how this can be done in other classes. So computational thinking starts with that first component of decomposition. Decomposition is taking a problem and breaking it up into smaller parts. So if you're a teacher and you're asking your students a question or you're posing a problem, then the first thing that they usually do is, look for that key information and break the problem into its parts. In English language arts, this can be done pretty effectively when you're studying something like the plot mountain. So if I'm giving my students a reading passage and I want them to find the different parts of the story and see kind of what was the exposition, the rising action, the climax, etc., they might decompose that passage. I might also do this in grammar, or if I'm doing a writing lesson, I might say, we're learning verb tense. Let's decompose the parts of a sentence and identify the verb. We might talk about the different parts of an essay and how a quote plays a role in an essay. So we might decompose our paragraphs and look at our introduction sentence and then our supporting details and decompose our writing. In science, this can be done with processes. So you might study things like photosynthesis or the nitrate cycle and see, okay, what are the different parts that, lead up to photosynthesis? How does a plant create its own energy? When you study things like the parts of a cell and compare and contrast, animal and plant cells, you decompose the cell and look at the different parts and what those functions of those different parts do. So instead of giving my students, the plot mountain and going through and defining each part, I might kind of have them start by looking and kind of seeing, can they pull apart the story into parts? What do they notice about a story? Or what do they notice about these plant cells? Can they look at the different parts and kind of see how they make up the greater cell before we even go into defining those parts? So decomposition makes a great anticipatory set. The next part would be pattern recognition. Once you have that data, once you have that information and you've broken your problem into smaller parts, then you start looking for patterns. We do this oftentimes already, but we don't always think aloud, or we don't always explicitly model for students that that's what we are doing. And sometimes we tell students the patterns before letting the students find the patterns. So pattern recognition is personally one of my favorite parts of this process because I think it really helps promote that higher level thinking. Students are able to identify patterns. So this might look like comparing or grouping or identifying or even sorting. So oftentimes this is done with literature studies when we study genre. So we look at fables and then we notice, okay, what are the patterns that we notice in all of fables when we're studying that? Is there something that's in all of these fables, and kind of what do we notice about that genre of literature? Even studying good persuasive writing patterns. So I might give students different persuasive essays and we might rank them and decide, okay, which one was effective. So we're doing that higher level evaluating skill. And when we find those effective persuasive writing essays, maybe then we look for some patterns and we decide, okay, what made this more persuasive than this essay, for example? So instead of just teaching my students like, hey, write a good hook, find some good evidence, here are some good sentences that are persuasive. Instead of doing that, I'm having the students come to those conclusions by looking for patterns. In social studies, history is somewhat cyclical, so this can be done when studying different events, even within the same time period. So if you're studying the Revolutionary War and all the different events that happened, there's a lot of patterns within those events that kind of lead up to the Revolutionary War. So having students kind of look for those patterns as you're studying a bigger unit. That can be a way to just build in that pattern recognition in your class. The next component of computational thinking is, I skipped one, is abstraction. So oftentimes students are doing this and they don't always have the vocabulary to describe what they're doing. So abstraction is the process of filtering out unnecessary elements or unnecessary information so that you can really focus on what's important. Going back to that writing example, sometimes we look for, when we're persuasive writing, we're looking for quotes to help us, back up our point or back up our idea. So when students are doing research, they have so many good quotes, they have so many good ideas, they've really got to, get it concise in their essay. So it's abstracting from their brainstorm and picking out those important key elements that will help them write their final essay. When reading, sometimes we're looking for that evidence that supports an author's point. So same thing, you're abstracting the details on the different facts in a nonfiction work and kind of deciding what are the key important facts that prove the author's point. In social studies, when you're studying a really big unit, there's a lot of different events. You can kind of, if you're trying to kind of refocus your attention on one thematic part of that event, you might abstract and kind of pick out which events to study that really align with the theme of what you're studying. And then even when you do those project-based learning tasks, at the end of a unit, I oftentimes would give my students these big research projects or these real-world problem-based learning activities, and my students sometimes kind of got down a rabbit hole. So sometimes we would have to use abstraction to really refocus them. So we might look at their project and kind of look at some key information that they have and kind of help them refocus their idea. So that skill of abstraction happens all the time, whether in what we're teaching, but we don't always have that vocabulary. So if we can start using some of this terminology, especially cross-curricularly and especially in different grade levels, then students will have a better vocabulary to explain their thinking and to use strategies when problem solving. So then finally, with computational thinking, that process, and you can kind of see that coders, this is exactly what they do, and they're writing code for our programs or code for our apps. Software developers, this is how they go through that process to write their software. Once they go through all of these almost like pre-steps, it culminates with this idea of algorithmic design. And so trying to get our students into this way of thinking where they're the ones creating the algorithm at the end of the day, that's going to help our students just be more critical, be more creative, and be more innovative. So algorithmic design is kind of at that end process of computational thinking. Now, math is something that we often write algorithms. So when you have a problem of the week and you're studying it, and you're even in kindergarten, if you're trying to count the apples, you write an algorithm for how you count. So, plus one, plus one, plus one, plus one. Essentially, that's an algorithm. But we're trying to look at this in different subject areas. So I really like this definition where it's a sequence of steps or instructions or rules to perform a specific task. So let's say a specific task is identifying the climax of a story. I always define that as the turning point. My students had a really hard time. They sometimes thought of it as the most exciting part of this story, and it was really hard to kind of differentiate and really find out, okay, what is the actual turning point of this story? So after kind of studying plot, I would sometimes have my students write an algorithm for how you determine the climax of a story. So they might write that sequence of rules or that sequence of steps. Now, what I really like to do is, after they wrote their sequence of steps, I would give them a different story and see, could those same sequence of steps be used in a different task? So they have to use the same algorithm and follow their steps, but with a different story. right? So it's like a similar task, but different data, different information. So then they could really test their algorithm and see, okay, was their algorithm specific enough or was it too specific? They could kind of debug their algorithm in that way. I also really liked having students trade algorithms. So I'm going to switch it over to a writing example. Sometimes I would ask students to write an algorithm for how you write an effective introduction paragraph. So they could write an algorithm for those steps, like here are the steps that you would take. Instead of me telling the students the steps and instead of me instructing the students, they're the ones creating the algorithms. So they're the ones that are able to really have that learning stick. They're following their rules and their set of instructions. What I would like to do then is have students trade algorithms and try each other's and see, okay, did that work well? Like if I follow this student's steps on writing an introduction paragraph, can I write an introduction paragraph? So I like embedding that collaborative opportunity and that opportunity to work together and debug each other's code, essentially. In social studies, this algorithmic design could be like writing a flow chart for the causes that lead to a big event in history. So what was like the sequence that had to happen in order for this bigger, larger event to happen. So instead of me giving the timeline and instead of me saying, hey, students, these are the important events, I might ask my students to create the algorithm that led to the Revolutionary War. And that kind of was more fun for them. They felt like they had more ownership over their learning and over how that process made sense to them. In science, this could look like creating a procedure. So you're creating an algorithm for something you're trying to solve, so that big question that you have. And then, again, maybe trading procedures and seeing, can someone else follow your same steps? So in the classroom, it's really important if we have these young students, we want them to be higher level computational thinkers. We essentially have to just give opportunities for students to engage in this way of thinking. So instead of defining things for our students and telling students the algorithm and telling students, these are the steps that you take to do X, having students come up with those steps and kind of probing them, giving them questions that lead them to those conclusions. So this sometimes takes perseverance. Students might not get the algorithm correct. They might be on the wrong track. So again, if they're on the wrong track, use abstraction, refocus them. Look for patterns on, why are they on the right track? So as a teacher, you're using computational thinking to give feedback to your students even. And then obviously too, just giving that collaborative opportunity for students to work together. Students can, co-create an algorithm. They could create an algorithm as a group and then compare with different groups. So I just think, sometimes we rush through objectives and give the information right away and then go on to the next learning objective. So with that perseverance piece, it might take longer, but students are going to remember it better. It's going to stick in their mind longer. So if they're the ones doing more of the thinking. So just some best practices, pose questions. So get your students thinking, get them creating and generating ideas. Don't just give them the definitions right away. Give them time to tinker and to solve a problem. Give them time to work out ideas and to draw conclusions before kind of giving them that answer right away. And then even as a teacher, sometimes be open-minded and be ready to accept more than one solution to a problem or even more than one algorithm. So I loved this in math, especially when I would sometimes use algorithmic thinking for students to create an algorithm to sort shapes, so especially quadrilaterals. And I would ask them, okay, if I gave you a shape, how would you classify it on the hierarchy? What could be your algorithm that could work if I give you any shape to make sure it gets categorized the correct way on the hierarchy? They would have to write those steps. Well, some students had just like such creative ways of taking that problem and writing those steps down that I wouldn't have even thought of. So just being open to more than one solution to a problem is also key. And I love these graphics. You can see I cited the source. The UK has a ton of great resources on computational thinking. But I love those different verbs that come to mind. And like I said, you don't have to create a whole new curriculum or go out on Teachers Pay Teachers and download a bunch of new worksheets. You can take our essential questions that are on the unwrapped documents and have those be your questions that you pose, and have students kind of create algorithms to answer those questions. Have them create sequences of steps, or have them create the rules for what you're studying to align with those big essential questions. So there are some resources for getting started out there. I'll try to link to those. So if you are just wanting to kind of introduce it in the beginning of the year with your students, or maybe do a less high stakes task to kind of get them familiar with the vocabulary, there's some great kind of fun, high level, high engaging activities out there that are free. I always really liked this graphic organizer and using it to create my procedures at the beginning of the year. So when I have my routines and I'm doing my classroom management, I would sometimes have the students write the algorithm for what it looks like to come into my class and be prepared and be ready to learn. So whether that meant the algorithm for them when they're at home, or if it meant the algorithm from the time that the bell rang and they had to get ready for my class, they essentially wrote the sequence of steps. And so in the beginning of the year, we started right away introducing these ideas of decomposition and pattern recognition and abstraction. And essentially, we wrote all of our classroom procedures and routines using computational thinking as a class. So that got them familiar with the idea and with the culture of my classroom, knowing that they had the ownership, they had to do the thinking. I was a facilitator, but they were going to be the ones that had to do the thinking in my classroom. So that was a great way to kind of get the year started with my kiddos. So hopefully this was kind of beneficial for you today. When we think about computational thinking and the future of our students and the jobs that they're going to have, they can't escape technology. So we know that this way of thinking is going to be essential for students who, enter the technology field. And even if they're not in the technology field, technology is in our lives all around us. So just being able to be critical thinking and creative thinking, the ability to debug something and kind of find solutions to problems, that's something that can be done with or without technology. So I just kind of want you to think about these skills and think about how it applies to your teaching already and how it can apply to your teaching going forward. And how can you apply this to your classroom today? Thank you, and I hope that you reach out if you have any questions, concerns. I would love it to hear when lessons go really, really well and your students have a lot of learning. I also like to hear when they don't go well and kind of work with you to kind of think, how could we do this differently, or what could we do in the future if a lesson tanks? Because, hey, we've been there and it definitely happens. So let me know, and I'd be happy to be a resource for you. Thank you all for participating in our PD on computational thinking.